function is a function that has a variable as it has a variable that's an exponent, and the base is always a constant. Base is a constant.
Is it? Are you saying x in exponent base? Exponent base. Oh.
All right. Is the first one an exponential function? We say no. What about the second one? Yes. What about the third one? Yes. Now, what's the difference between the second and the third? One of them is actually a growth, and the other one is a decay. Which one is the growth? The second one. When the number is bigger than one, this is a growth. When the number is bigger than one, the third one. Yes. And the one that has a number smaller than one is a decay. This one will grow, this one will get smaller. All right, let's start by graphing the parent function f of x equals 2 to the power of x. Let's go ahead and graph it. Y equals 2 to the power of x. You can use your calculator to put this in it and go to the table. Once you put 2 to the power of x on your calculator, you don't have to have this 0 for now. I want you to go to your table, and under your table, mine does not start at 0 as I want it. I go back to table set, and I ask it to start at 0, and I take it back to my table. On the table, for 0 is 1, 1 is 2, and so on. So that's what you're going to copy on your paper, these values. So what do y'all got for negative 2? 0.25. What do y'all got have for negative 1? 0.5. For 0 it should be 1. For 1 should be 2. For 2 should be 4. And for 3 should be 8. No, it's not doubling. Not always. Not always. Now, here's what you got. Let's go ahead and try to graph it. So if you graph it, you will notice that it will look like this. Something like this. Is that what y'all got on the calculator? Huh? It's steeper.
It doesn't go as, yeah, it just goes that far. It doesn't really go like.
It's steeper, that's all.
Well, doesn't it end?
It doesn't end. Never.
Well, it looks like.
Think about this. Can you stop the values that you can put in for x?
No, but it's just like on the calculator, it looks like it's stopped.
Unfortunately, the calculator is limited. It can only limit it limits to 10. All right. There are two types of exponential function. One of them is called growth, and the other one is called decay. A growth is when we call that constant is when the constant is what? Greater than 1. Greater than 1. Equal, then it doesn't change. I mean, that means it's 1. 1 to any power is 1. Keep that in mind. Now, this is when the constant is less than 1. When the constant is less than 1, and when the constant is greater than 1. Now, for example 1, we will try to find if it's a growth and or a decay. And you have your calculator to help you. So I'll go ahead and put that on my calculator. 5/3. Yes, ma'am. Once the other two return, I don't know why they're still out. It's 5/3 to the power of x. And let's go ahead and graph it. Nope, I didn't put the power. Look how it looks like. Now, is it a growth or a decay, by the way? It's a growth. Why is it a growth? This is another way to figure it out. By the way, you're not looking, it's not based on the graph necessarily. Look at this, 5/3. If the number on top is bigger than the number on the bottom, it means it's bigger than 1. So if you divide 5 by 3, we each have at least 1. Yes, therefore, you will say 5/3 is greater than 1, therefore it's a growth. Then sketch a graph. If you want to sketch it, go ahead and sketch it. It looks like this. Remember, the sketch is not 100% accurate. Let's look at example 2. Obviously, this is a growth or decay. Decay. 0.2 is less than 1, so I will say it's a decay. Sure. Now, let's just graph it to see how different it is. So, I will graph both of them on the same graph. The next one is, can you read that function for me, please? 6 times what? 0.2 to the power of x, right? Let's graph it. And this is how it looks like. You see the difference? Is it growing or is going down? Pretty much growing side from left to right, it starts small and it goes up forever. Decay side big and goes down forever. Decay means it's going smaller and smaller. Who can give me a good example of a decay function in real life? No, people don't, there's no decay on us.
Money in a company.
What was that? Temperature? No. Depth? No. Depth is usually growth. What? Alignment? Climate? Decay? No, it kind of fluctuates. It's not a decay.
Acceleration.
Who?
Acceleration.
Acceleration? That increase and decrease completely. Another one. There's one very common one.
Health decay in people has like 50, I guess.
Health?
Yeah, like
Well, it might not be exponential. What was that? Age, it grows though. Then it can be a linear function growing up forever. Yes. What? A virus can be, it depends. If it's on in biology, you will have an exponential growth there. Here's a very simple exponential decay. The value of a car. The value of the car will decay exponentially. The first day you buy it, take it out of the dealership, come back, the value changed already. That's an exponential decay. Example 3 says, by the way, exponential decay will start up and goes closer and closer. So just by looking at the graph, can you tell if it's a growth or decay? Yes or no?
Yes.
I hope so. Example 3 says, Jill invests $5,000 in an account that pays 6.25% interest per year. After how many years will her investment be worth $10,000? Do you remember the formula for this? Is A equals what? There are two formulas. A equals PE to the power of RT. No, thank you. And A is... One of them is A equal PERT, and the other one is equal to A is equal to P times 1 minus R over 1 minus... I just went blank. So the first thing I would do is identify every single element. 5,000 represent my P, 6.25 represent, actually it's 0.0625, that's my R. Per year, the fact that they say per year, it means that N is equal to 1. So I can summarize this formula and say it's A equal P times 1 plus R to the power of T. In other words, all I did was changing N into what? What's the value of N? 1. Changing N to 1. After how many years? That means I'm looking for a time. With the investment worth 10,000. 10,000 represent my what? That's my A. So let's go ahead and plug in the values that we know. I will say 10,000 is equal to 5,000, 1 plus 0.0625 to the power of t. First step is to divide both sides by 5,000. And if you divide by 5,000, you will end up with 2 is equal to 1.0625 to the power of t. This question is for Gerardo. Is it a growth or a decay? It's a growth. The value is bigger than 1. Very good. So, how will you solve for t? It's not the root. Guys, have we done logs here?
Yes.
Yes, you did. We did. Drop the base and switch. We have not?
No.
No? Yes, we did.
No, we haven't.
Okay, if we haven't, y1, y2. So why don't we do it? On the y1, all I would do is put 2. And on the y2, I will put what? 1.0625 that I raised to the power of x, right? And I will just graph it, and this is what I see. Well, they kind of go together, but all of a sudden our exponential function will start growing, and it will get close to the other one. You see how close it gets? Now, we are not seeing when it touches. So to see when they will both meet, what do I need to increase? My x value. So I'll go under my window, and what do you want me to increase my x max to?
20.
Only? Let's go high, 50. And I'll graph it. Maybe 20 would have been enough, but I went to 50. And this is what I see. I know your calculator is not showing Decay colors, but who cares? You can still see them, right? So from here, I will do second trace. Second trace 5. Enter, enter, enter. It tells you that it's after 11.43. And that's in years or what? Or months? In years. So you will say 11.43 years. So t is equal to 11.43 years. Now, since they say 11.43, that's exactly after how many years would that actually reach? Let's think about it. Will it be 11 years or 12 years? 12 years, because it will not reach after 11. And 11.43, you won't make payment till the next year, so it's after 12 years, to be for common sense. Now, using the log, although you say you have not done it, it will be log base of 1.0625 of 2 is equal to t, and you will put that on your calculator. We're gonna get to the log if we haven't worked on it yet. Let's look at problem number 4 now. It says in 1981, the Australian humpback. Would you like to read for me, Freddie? Please? Thank you.
In 1981, the Australian humpback whale population is 350 and increased at a rate of 14% each year since then. Write a fraction of the model population growth and use a graph to predict when the population will reach 20,000.
Okay, let's first identify what each information is. What does the 350 represent? A, P, R, or T? It's a P. What is the value of R here? Nope, it's not 14, but 0.14. Why is no O? Because imagine you divide 14 by 100. Go ahead on your calculator. The other one we had an O because when you divide it gave us an O. But here's the trick. When you divide by 100, move the decimal place, the decimal point, 2. 100 is 2. From here, 1, 2. On the previous one, if you move 2, you will create a 0. All right.
What is he supposed to stand for?
The principal, the starting. And A is the final, meaning 20,000. We want to write the equation. The equation is A equals P 1 plus r to the power of t. Let's write even what we know. Use a graph to predict when the population will reach 20,000. Now remember, A is something that's for the second portion. So all we know is A is equal to, P is 350 times 1 plus R will be 1.14 T. This is the equation. Now, let's use our graph to predict it. I'm coming back to it, Erica.
Okay.
What's the first value that I will write here? 20,000, right? And what's the equation? 350 times, is it 1.14? That I'm raising to the power of x. Well, the x is there already. Now, one way of going straight to where they meet is to do zoom what? 0. Zoom 0 is the zoom fit. It might show you where they both meet already. So let's see. That it did it. Good try. Actually, yes, me. Zoom 0 gave us where they meet. So all I have to do is second trace 5, enter. It's after 30.87 or 30.88. So I will stay here 30.88 years. But yes, it's going to be 39 years. It's growing, so it's after 39 years. Remember, there's a common sense behind it too. Since it's a word problem, 30.88 years we won't reach it. It's after 39 years. 31. And I copy you. That's 31. It happens. Now there's one for you to try and let me know how you do on that.